Welcome PCS members and our friends to our Tuesday IBS PCS seminar. It is a great pleasure to have with us today Dr. Archak Purkayastha, and I would like to invite our scientific host, Juzar, to introduce our speaker. Please, Juzar.
Thank you, Tilan. It's a great pleasure to introduce Archak, who's been a friend for a long time. Archak got his PhD in 2018 from ICTS, which is the International Center for Theoretical Sciences in Bangalore in India. This was under the supervision of Professor Abhishek Dhar. After his PhD, Archak moved to Dublin, Ireland, to join the group of John Gould at the Trinity College. After a short one-year stint, he received the Marie Curie Fellowship, where he continued in the group of John Gould and also was then associated with Professor Javier Pryor in Spain. Archak is an expert on open quantum systems and non-equilibrium quantum statistical mechanics, thermodynamics, and has recently gone into several numerical techniques to study quantum many-body open systems. With that, I would like to give the floor to Archak for his talk on classical simulation of quantum devices. Archak, the floor is yours.
Thanks, Juzar, for having me here, and thanks for the nice introduction. So I'll be talking about classical simulation of quantum devices, meaning that it's simulation of quantum devices on a classical computer. So let's first look at some building blocks of quantum devices, right? So what we have here is something called molecular junctions. Now, these are very commonly used in many sort of quantum devices. It's like some small molecule connected to two sort of bigger, much bigger molecules where you can define some temperatures and chemical potentials. And so you can bias this flow through the molecule and so on. So what we have here is something called a double quantum dot. Okay, so this is some solid state device with these. There are various leads here, and using various voltages in these leads, what you do is what is done experimentally is like we confine some excitations in these two sites, sort of, right? So, and that becomes two dots. Okay, so this is like double quantum dots, and then this is probably the most well-studied and the classic sort of building block of a quantum device, which is just an atom or a two-level system in a cavity. Okay, and then it is driven by some light and some output is measured and so on. What we have here is essentially a realization of the same thing, but on a solid state circuit. Okay, where there are some LC circuits that act as this kind of a cavity and so on. And all the sort of existing quantum computers that one can now access online are sort of built on this architecture. Okay, so what are the some common properties of this kind of quantum devices, right? So first of all, they are very small, and as a consequence of being small, I mean, they cannot be completely isolated from surroundings. Okay, so inherently they become noisy and dissipative. Okay, now the next thing is their working principle is typically by driving them out of equilibrium. So like here you put some voltage bias and you go look at some currents. Here you put a drive here and look at what is coming out and so on. So they fall under this sort of big name called like driven dissipative quantum many-body systems. Now to understand quantum devices, we need some theories or some numerical techniques for this kind of things. Now, experiments have, of course, like made tremendous progress in realization of various quantum devices recently, right? However, most state-of-the-art theoretical or numerical techniques are limited to these regimes. So what is like either infinite temperature or zero temperatures, small non-linearities, like if the system is linear, you can do a lot of things, but if the system has some non-linear terms, which I will refer to as interactions later, right? Then it's difficult. Then you can assume like weak coupling to environment, which is not always true. Like in the molecular junction thing that I showed, I mean, these couplings are usually strong, right, in experiments. And like very small voltage bias or very large voltage bias, like linear response regime or like infinite voltage bias, these kinds of things one can do. Like most state-of-the-art numerical and analytical techniques are like this. And apart from this, except for these cases, like infinite temperature, like most of these, even the things that exist, most of them are not sort of scalable to large systems. They are limited to like a single qubit, a single impurity, and so on. But a device can consist of a large number of these things, right? So experiments do not satisfy any of these things many of the times. And what this limits us is our understanding of already what can be realized in experiments. We can realize them, but we cannot understand them. So, and this is exactly why we need a simulation technique, which is valid for a wide range of parameters, which are accessible in experiments and beyond these limitations, right? Now, why is it so difficult, right? Why don't we have a theory like that? So the problem is, first of all, if there are many-body systems, there are quantum many-body correlations. And then these systems typically, in presence of this kind of environment, this system will typically relax, okay? But they often take a long time to relax. So if you want to study, if you want to make some theory of these things, you have to sort of look at the dynamics for a long time, then that is a big problem. And the other problem is it's generically non-Markovian, usually with a finite but non-negligible memory time. So if you don't know what non-Markovian is, I'll explain in a little while. So these are sort of some of the things that a combination of these things make it very difficult to do any kind of numerics or analytical techniques, right? So now let's go to a more concrete formulation of the problem. Like, how do you think about these things? So I'll mainly be looking at this kind of setups, right? Something small connected to something big at the two ends. Okay, so you can think of these kind of setups as something like this. So this NS means like the number of particles, right? All the N's means number of particles, and these are the Hamiltonians. So you have some small system here, which is, let's say, this way, right? And some big systems here. So everything is described by some Hamiltonian. Now, of course, the small system is not isolated from the big system, but we can assume that the big system, the full thing, is isolated from the rest of the universe, right? So that's the full isolated system. So you have a full Hamiltonian like this. Now you have to encode in the temperatures and chemical potentials, like temperatures and voltage biases. So how to do that? So the standard way to do that is to assume that the state of the system, so the state of this guy or the state of this guy, is arbitrary, but the baths, so these are called the baths, okay? The big systems are called the baths. They are in the thermal states with their own temperatures and chemical potentials. Now they can be different, right? So that's how you encode temperatures and chemical potentials. The system is finite, but the baths are in the thermodynamic limit, okay? So with this, what you do is just you time evolve this full thing. So that's some dynamics going on, but we are looking at only the system. So we trace out the bath degrees of freedom. So this gives me a density matrix of the system at time t. And this is a notation for the same. So this is a notation for carrying out this process essentially. And this is sometimes called a completely positive trace preserving map, a CPTP map, from which takes a state from this time to a different time. So if you look at, if you want to write down an equation of motion for this density matrix, it completely generally, like it's without any approximation, it has this kind of a form, okay? So you see, this term is the usual term that you would have if you are completely isolated. This term is the term that appears due to the connection with the surrounding environment. Now this, look at this term. So this K is something, this is a notation again, it's a notation exactly like this, where this K is like something being done on this density matrix. So this is like a super operator. Okay, you see that this term depends on the whole history of the density matrices. Like it's like essentially at all times starting from the initial time, right? So this is what it means by being non-Markovian. Okay, this is a term that would not have been in an isolated system. So that is a source of a problem. So usually when I said like there's a finite memory time, it means that instead of t minus t naught here, you can upper cut off this with some finite time. But still, it's not Markovian in the sense that this term is there. Okay, so the goal is to obtain the dynamics of this density matrix as exactly as possible, and when there is no small parameter. So that is a very challenging goal, and especially when this system is a interacting quantum many-body system.
Archak, we have a question. Dilip, please ask.
Yeah, so maybe just a basic question. So the density matrix for the bath you have written, so it should be like a tensor product, right? Between two.
Yes.
So it's not just a simple product, right?
Okay. So, okay. I mean, usually, so even when you write like something like C1 dagger C2, it means a tensor product. So between C1 and C2, right? I mean, so that's
no. I mean, even if you have this density matrix for the bath only, you have at both sides you have two baths.
Yeah. So I mean, this IL means tensor product here, right? I mean, essentially.
Oh, okay. Yeah. Oh, yeah. I got confused. Yeah. Thanks. Yeah.
Okay. So this is the setup. This is the problem. So how this is the problem that like this is a fundamental problem of open quantum systems, is actually just calculating this density matrix. So what are some of the techniques that are used to do this? So by far the most common technique is Markovian quantum master equations. So when you don't consider that non-Markovian thing. So I mean, usually you say that, okay, for some reason there is no memory. Okay, and that can be justified actually only in weak system path coupling or infinite temperatures. Okay. And very often you just write it down phenomenologically, and it's in some so-called Lindblad form. So that this is the so-called Lindblad form. So this is a Hamiltonian term that's coming due to coupling with the baths, and this is something that doesn't look like a Hamiltonian. So this part is called. So these operators are called Lindblad operators and so on. So the problem is, if you write it down phenomenologically and you are trying to describe an experiment, you find some parameters here that describes the experiment nicely. Great. You change the parameters, you do not know that the same equation describes another experiment, that same experiment for different parameters, or another analogous experiment for different parameters. Okay, so there is no control over validity regime if you do it this way. Also, this is something that has been that we have recently shown, that this is actually like, so one way to justify this thing is like weak system path coupling, right? And the point is, in weak system path coupling, like it's just impossible that it gives all elements of density matrix correct to leading order. Okay, so there are some fundamental issues with it, but still it's a most popular one because it's numerically and analytically the simplest one, and also this is the one which is the most scalable. Okay, so I mean this is a textbook material, so I mean it's there in all textbooks, and there are many works showing scalability. This is one of the recent works. Okay, I mean this is not the only one, right? There are many works. So you can just make a chain of like 1,000 qubits or like 100 qubits and do these things. Okay, so this is one. The next method is probably not so popular, but has been around for quite a long actually. Okay, it's called collisional models or repeated interaction schemes. So this is like instead of, so we had this bath in the thermodynamic limit, right? And this says that, okay, forget about it. Let's do something simpler. Let's do a bath with just a 1 qubit or 1 mode or like a few modes and so on, which then repeatedly interacts with the system. Okay. Now, if you write down some phenomenological Lindblad equation, the reason this became popular again in recent times is because if you write down some phenomenological Lindblad equation, you can derive any Lindblad equation from this kind of an approach. Okay, so the problem is now, so this basically gives you, so Lindblad equations had some problems with consistency with quantum thermodynamics, and this technique has been used to sort of reconcile the Lindblad equations with thermodynamics, right? And since you can go to this Markovian limit in a systematic way, you can also systematically go out of the Markovian limit if you want. However, the problem is, like, if you really wanted to describe this setup that I showed in the beginning, meaning with baths in the thermodynamic limit, so if you go beyond the Markovian limit, you get some dynamics, but whether that dynamics actually corresponds to the dynamics that you actually wanted to do in the beginning, it's not sure. Okay, so that's the problem of this kind of approaches. Okay, so then there are these set of techniques, and these are the go-to techniques for any non-Markovian analytical treatment of any non-Markovian systems. Okay, so these are there is something called Keldy-Schwinger also, which is also like part of all these things, right? Okay, so if you have a linear system, so this is what I meant by a linear system. So if you have the full Hamiltonian of the system and the baths and so on, if you can write it like this in this form, then the equations of motion will be linear. Okay, and for such systems, these techniques can give you exact results. Okay, for steady state. Now, if you want to look at the dynamics of approach to steady state, it's a bit more difficult, but still can be done. Okay, but if you cannot write your Hamiltonian in this form, okay, then those terms need to be, you have to treat them perturbatively, or you have to do some perturbative treatment. So you need a small parameter. So if you don't have any small parameter in your problem, you cannot use these things. And these are again very textbook things. So you can find textbooks, and there are some. So okay, Juzar is one of the authors of this paper. So those are all the sort of analytical to some extent techniques, and then there are these numerically exact approaches. Now these are really like numerically exact, meaning you have some parameter in your numerics which you can increase or decrease systematically, and you will decrease that will systematically decrease the error in your calculation. Like if you want accuracy up to this many places of this many significant figures, you have to increase or decrease the parameters, and then you hope that within your computational capability, you can make it converge with those parameters as much as possible, right? So this is what I mean by numerically exact techniques, right? So there are like I have mentioned like here like 3 classes of things. So one is like memory storing technique. So I said that okay, you have a finite memory, so you can maybe store that thing to up to a finite, that integral up to a finite time and do something. So these kinds of techniques have been formulated using this Feynman-Vernon influence functional. Okay, and then there is something called transfer tensor and so on. So these are 2 references for that. And then the other thing is, look, the most naive thing you can do. Okay, say that okay, I cannot simulate a bath in the thermodynamic limit, but I can take a finite but large enough bath and do a brute force simulation. So this is one work which is like that. And then there is something called hierarchical equations of motion, which has been again like which is again sort of exact, but again it requires more and more sort of computational resources. And so due to limitations of practical implementation, all of these techniques, okay, can either give dynamics up to a finite time, or limited to small systems like again 0-dimensional systems like single qubit, single utility, and so on. So all of these techniques are like that, right? And then there are a slightly different set of techniques, which goes by various names like mesoscopically, pseudomodes, sometimes called driven Liouville von Neumann, and this name is usually popular in quantum chemistry. Okay, so this is slightly different. here says, okay, the bath is infinite, something in the thermodynamic limit, but we cannot do that. So we'll take a bath which is finite, and we'll add to each bath mode Lindblad dissipator. So I'll phenomenologically do that and do it in such a way that this fictitious Lindblad equation has the same non-equilibrium steady state as the original setup. Okay. Again, this is again sort of numerically exact, because if you keep on increasing the number of modes in the bath, you know that it will converge, and you want how much you can converge and so on. So these are some references for that. This technique has been recently shown that it can be extended to it is actually scalable to large systems. Okay, so this is one paper where we have done that. However, the problem here is that with a finite number of modes, right, in the finite size bath, it's not clear that the dynamics of approach to the steady state is going to be correct. So you can get the steady state probably very correctly. Whether the dynamics will be completely correct is not clear. Okay, so the summary is that we have these kinds of techniques limited to weak system bath coupling, or these are essentially just toy models. We do not know the essential some validity regime of these things, especially not beyond, like we do not know if they represent some baths in the thermodynamic limit beyond the Lindblad regimes, and these require some small parameters. And then other techniques are, the numerically exact techniques are either limited to finite time or limited to zero-dimensional systems, or gives exact steady state but not dynamics. So right at this point, it seems that obtaining full dynamics of steady state of an extended quantum many-body system is intractable via any present theoretical or numerical technique. So the work that I'll be talking about now is basically telling you that not anymore. Okay, now you can do this, and how to do that. So this is the work. It's been recently published in PIB. The statement, the breakthrough statement is this, right? If, so not under all circumstances, but if the non-equilibrium steady state, so NESS is an acronym for non-equilibrium steady state, is unique, then in almost all cases, the full dynamics of an open quantum many-body system can be reconstructed by repeatedly using evolution up to a finite time, requiring only finite-sized baths. Okay, so we call this technique periodically refreshed baths, or this formalism. Okay, and the acronym is spread. So why does this change everything? So I mentioned there is this numerically exact techniques that allow simulation up to a finite time. Okay, so now what I'm saying is we can use those things and then recursively use those things to reconstruct the full dynamics up to steady state. Okay, so that's one thing. The second thing is, if you remember, I spoke about this brute force techniques, right? And this brute force techniques are essentially you take the system as a system and the baths as a large enough system, large enough isolated system, and then just evolve the full thing. And then you do not need any open system tricks, right? You need some standard techniques for dynamics of isolated systems. And since you need finite size baths, you can use those tricks to do the dynamics.
Archak, we have a question. Chung-Yun, please go ahead.
Hi, I have a question. How do you check whether non-equilibrium steady state is unique or not? How do you check this?
No, you don't. Yeah, I mean, you don't. It's a very difficult question, actually. We don't know. In certain cases, you can. Usually there will be a unique non-equilibrium steady state, but yeah, it's not very easy to know that there is like the cases where there is no unique non-equilibrium steady state are actually rarer. So you have to sort of look for this. Yeah, that is not known. So yeah, so if you a priori expect for some physical reason, if you're in your system that you will have a unique non-equilibrium steady state, or if you a priori have some experiment where you know that there is a unique non-equilibrium steady state, you can use these things, this approach. But otherwise, if you do not know, you know that yeah, just hope that it works. Otherwise, if you know that there is no non-equivalent steady state, then this approach will not work.
Yeah, then why do you need this condition? Will you tell this why this uniqueness is important?
Probably, if you can converse this technique, probably it means that there is a non-equivalent steady state. But yeah, that's a bit of faith in the technique, though.
Yeah. Okay. Thank you.
So yeah, I mean, I'll come to this precise statement in the next slide.
We have another question or comment from Varinder. Varinder, please go ahead.
Hi, Archak.
Right.
Yeah. So, what do you mean by like NESS is unique? Does it mean we don't have multiple steady states?
Yes.
Okay. So, means your formalism will not be valid for like degenerate systems in which we can have multiple steady states.
Degenerate meaning in degeneracy in what?
In degeneracy in like system, like in system degeneracy. So if
no, I don't think system having degenerate levels probably has. I mean, it's not directly, that does not directly translate to having not multiple steady states in non-equilibrium steady states in coupled to baths.
Okay, but actually there are some systems like 3-level systems, like in SSD model of heat engine, Scoville's model. So if like system has degeneracy, then it might have, you can say, multiple.
No, so I mean, I think these models are, I don't know. Okay, I don't know exactly what you're talking about. But I think I mean the kind of descriptions I think they are all either in Lindblad equations or something like that. So maybe in certain limits, but whether if you connect to these kinds of if you do a more microscopic modeling, whether it has a unique steady state or not is actually a hard problem. It's not a general. It's not very easy to see actually.
Okay, maybe it is. Then my question is related to a particular model. So I get your point.
Yeah, but if you know that there is no unique steady state, then you should be wary of using this technique. But then you have to sort of. So I mean, let me go to the next slide. I mean, the thing is like we could prove this thing assuming a unique steady state. Now, whether if you don't have a unique steady state, whether this works or not, we had one system where it does not work, but otherwise it requires a bit more exploration whether this can be extended to at least some cases, but we don't know.
Okay, thank you. Go ahead.
Okay, so this is the precise statement actually. Okay, so exactly, I mean the uniqueness of the steady state and the dynamics is analytic, and the Hilbert space is system Hilbert space is effectively finite dimensional. Okay, this can also be effectively, right? It does not have to be exactly. Meaning, if you have a bosonic system, you have an infinite dimension Hilbert space, but if the number of bosons per site is capped due to some physical reasoning, then also it's a finite dimension, right? So these three assumptions were required to prove this statement, and that's exactly what I mean by this is required. Okay. So this is the statement. So this is the thing that we are wanting to do, right? This is the density matrix that we want to calculate. Now, here is a different density matrix actually being obtained by a very different process. Okay. So what is this process? So what was this process? We had some state of the system and the thermal states of the baths, and then we evolved the full thing up to a time t, and then we trace out the baths. Okay. What is being done here? We start from the same steady state, same initial state, and then evolve this up to a time t1. Okay, then we trace out the baths. We get the state of the system. Now, what we are doing, what this notation essentially means that physically, it means that we are detaching the baths and refreshing them to their original initial thermal states at this point. Okay, and then we are again evolving doing a step like this with the full system plus baths, and doing this open system evolution for a time tau. Then at time tau, we again decouple the baths and refresh them to their original initial states, and we keep doing it n times. Okay, so the statement is that the difference between these two density matrices decays with tau. Okay, that's the statement. So in other words, that this density matrix converges to this density matrix on increasing tau. Now, what is the value of tau that you would require? So this is a proof, right? This is a mathematical proof, right? Now this part is not a mathematical proof. Okay, this is just a physical argument. So what is the value of tau that you would require to reach a reasonable convergence, let's say? So that value of tau is of this kind. So in the sense that, so there is TSS is some effective time to reach this non-equilibrium steady state in the full evolution, and tau m is the finite memory time. So I've been talking about this finite memory time, and that's this thing. And if your system, if your setup is basically describes a quantum many-body system, okay, an extended quantum many-body system with only few sites attached to baths, okay, then we expect this. And why do we expect this? Because we could prove that tau has to be much greater than tau m, and tau m can, and there can be wide scale separation between tau m and TSS in this case, actually, okay, because the time to reach steady state, if you have a big system with only few sites coupled to baths, the time to reach steady state will depend on how information travels inside the system and so on. However, this effective memory time, you can estimate it just from the bath properties. Okay, so these two things are very different, and they can have a very if you have an extended system with a few sites coupled to bath, these two things will typically have a very large scale separation, and then with some in between time scale we can converge this thing. The important point to note is that tau is much smaller than TSS. Now, whenever that happens, it becomes extremely advantageous, because we do not have to evolve up to the time to reach steady state, which can be very large. We have to evolve up to a finite time and basically just recursively use this trick here. So it will become more clear in the next step. And more, but before that, I want to say that this finite value of tau actually means that we can get away with finite size baths, at least for certain classes of baths. Okay, so, and which is the most popular classes of baths. So this is the most standard model of baths is something like this. Okay, which is like an infinite number of bosonic or fermionic modes. And the most standard system bath coupling is of this form, where S is some arbitrary system operator, but this bath operator coupling to the system is just the bosonic or the fermionic annihilation operator. Okay. Whenever this happens, it is an exact statement that the dynamics of the system is governed by these two functions. Okay, so this is called the bath spectral function, and this is the Bose distribution of the Fermi distribution corresponding to the initial temperatures and chemical potentials of the bath. Now, given any bath spectral function, okay, you can, so this setup, so if you have two baths, this setup is of this form, meaning, so these are the infinite number of modes that I have here, and each mode is connected to the system. Given any spectral function, so this needs to be a continuous function, right? You can always map this kind of a bath to this kind of a chain. Okay. Okay. So here I have a finite size chain, but if this is infinite, then this mapping is exact, meaning that, so you have a chain like this, so where the first site is coupled to the bath, and then there is just hopping between the various sites. And if this chain is infinite, then you go to the, again, diagonalize and go to the normal modes of the bath, then you get exactly these modes with these couplings and everything exactly the same. So there is a prescription to do this, go from this picture to this picture. Okay. You can look at this. This is a sort of this is a book chapter actually, but it's available on archive, and this has very nice discussions on it. So you get these on-site energies and these hoppings. Now the spectral function is encoded in these things, and typically what happens is that these things quickly tend to constants, and then this constant is directly proportional to the bandwidth of the bath. So there is one catch here. So you have to have a finite hard bandwidth. But if you do not have a finite hard, like any physical bath will have some bandwidth or some cutoff. But if you do not have a finite cutoff, you can you have an exponential cutoff or something like that, you can put a finite cutoff which is much larger than the exponential cutoff if you want, right? So you can always do this. Okay. Now, because of this geometry, okay, so the process that we are trying to describe is like we have some state of the system, thermal states of these chains, okay, and then we switch on the coupling and something is happening in the system and something is happening in the baths. That's what we want to describe. Now there is something called Lieb-Robinson bounds, which basically says that if you put a disturbance here, that only travels at a finite speed in such a chain. And because of that, if you want to simulate this entire thing up to a time t, you do not need actually an infinite size chain, but you need a finite size chain which is proportional to t times this hopping parameter. Okay. So now remember that we actually do not need to do a even up to a long time t, but some small time tau. So we actually can get away with a finite time, finite size paths. So let's look at how this looks with two paths. Okay. So this is the kind of setup that we want to model, right? So how do we model this? First, we take this thing, we map it to a chain. Okay. We have some initial state of the system. We evolve the full thing, and then trace out the paths. We have some state. Now, if this part of, if you have some black box, right, where you can do this evolution, you take some initial state of the system with thermal states of the paths are already given. You take some initial state of the system, and it outputs some final state of the system at some time by evolving up to a time tau, let's say. Then what you have to do is you have to just recursively use that same code, just using the output state as the input state for the next step. That's all you have to do. But this time evolution from here to here, you have to do it for a time tau. So the chain sizes that you need are just of this size, right? So that's not an infinite size chain. And if your time to this steady state was long, then you would have required, if you just did a continuous time evolution, you would have required a very long chain here, but you actually do not need such a long chain. So finite time and finite size paths is ideal for tensor network implementation. I'll come to that in later slides. So let's go to the numerical example. So yeah, so this is a numerical example that we will be looking at mainly. So this is, everything is Fermionic here. So you have a nearest neighbor tight binding chain. The hopping parameter is set to 1. So the everything is in terms of hopping parameter, right? And there is nearest neighbor interaction also. We'll come to the interaction later. Okay. The first side is coupled to a bath. The last side is coupled to the bath. A bath spectral function is chosen like this, which is very standard for Fermionic systems. And remember, we do not want any small parameter, right? I mean, the challenge is to do it where there is no small parameter at all. So the system bath couplings are strong. Okay.
Archak, we have a question from Jungyun.
Yes.
Hi. What do you mean by finite size chain? Because you consider indeed infinite number of modes of paths. So how do you implement finite size chain with infinite mode of paths here?
No, sorry. So you have a infinite number of modes. If you exactly map this, this would not be a finite size LB. This would be a infinite, semi-infinite tight binding chain with the first side coupled to the bath, and that's an exact statement. Okay.
Yeah. Mm-hmm.
Now we want to do a time evolution. So we want to take, let's say we have semi-infinite chains here on this side and this side. Right? Now we want to take do the dynamics of this full thing, where the chains are initially in the thermal states, and there is some initial state of the system, and then we just want to evolve the full thing. Now, in absence of the system, the chains would not evolve because they are in their own thermal states, right? So the chains evolve only because you switch on coupling between the system and the bath. So for the chains, it's like a disturbance that has been done at one end, right? And that disturbance is propagating inside the chain. So that propagation due to Lieb-Robinson bounds, it can happen only at a finite velocity. And that velocity is proportional to this hopping parameter here. So basically, if you want to evolve but we are not interested in the chain actually. Okay, we are just interested in the system. So if you want to evolve the state of the system up to a finite time t, you do not actually need infinite size baths. So this mapping from here to here would require infinite chains. However, if you want to when you want to do the dynamics up to a finite time t, you do not need infinite size baths to get the state of the system correctly. And that is a very rigorous, that has a very rigorous Lee-Robinson-Bound arguments on it. Okay. So that's how you can get away with the finite size path.
So you'd like to truncate number of sides of chain,
yes,
with given time domain what you have.
Yes.
Is it correct?
Sorry,
you'd like to truncate number of sides of chain.
Yes.
With given let's say given temporal window. Is this correct?
Temporal, yeah, exactly. So I mean that's what I'm saying. So this LB here is proper. I mean you need, so if you want to simulate up to a time t, you need baths of size t times this this hopping parameter, right? With some proportionality constant, but it's of that order, like some order 1 proportionality constant, 1 or 2. Okay. So the point is now this is now if you still want to do a long time simulation, right? I mean this still grows, right? So if you want to go to a like steady state and steady state is long, you still need a very long, very large bath size here. Right? However, with this refreshing idea, with this prep, we do not this particular step is only being done up to a time tau. So here for this particular step, we do not actually need a infinite size bath. We need baths of size tau times this hopping parameter again, right? Now the point is just by recursively using this trick, this let's say we have some kind of code here that does this. By recursively using that same code, we can get the full dynamics up to a long time without ever requiring large size baths. Okay.
Yeah. Okay. Yeah. Thank you.
Okay, so yeah, so this was the system, and then we have strong coupling to the baths, finite temperature difference between the two baths, finite chemical potential difference between the two baths, and this GB is taken as 2, and system size is not too small, it's 16. It can be much larger. This is just done for comparison. And if you want to look at what is the memory time, and this can be sort of estimated from the decay of bath correlation functions, let's say up to like when bath correlation will decay to some like 2% or 3% of its initial value or something like that. Its estimate can be estimated as something like 2. Now everything like all these numbers are in units of this hopping parameter. Okay, so let's look at the example. Okay, now this with a non-interacting case. So this V is equals to 0. So this was the V. This term is not 0. And again, as I said, then this entire thing can be written in that quadratic form. So this is a linear system, and this can be exactly solved using various tricks. Like one of them is just this, right? So you can where D is some either a bath operator or a system operator, like bath creation operator or a bath annihilation operator, system annihilation operator, and you create a matrix like this. This matrix will be LS plus 2 LB dimensional, which is just linear in the systems, like the system of full size system plus baths. So this can be done exactly, and the steady state can be found exactly using non-Markovian Green's functions. Okay, so we have exact results, so we can benchmark this thing. So this is the statement, right? And here we are checking that. So what is being plotted is occupation in some site, but it can be any other observable of the system. Okay. So first we have this continuous blue line, which you call exact here, which is basically this right-hand side. And it is done with, again, this chain mapping with a finite but large enough bath, so that you don't see finite bath size effects. And that's, you see some dynamics, and it relaxes to the steady state, and the steady state result we have from NEGF, right? Okay, that's with infinite path. That's analytical calculation. So yeah, so that is the right hand side is fine. Now let's look at this refreshing idea. Okay, the first first of all, here T1 is 0. Okay, for this one T1 is 0, and we have, let's use tau equals 3. Now for tau equals 3, you need a bath size of 8, meaning that if you take any larger bath size, you get exactly the same result. Okay, again due to Lieberman bounds. Okay. So you get this orange line, which is definitely different from this continuous line. Right? But this is supposed to convert with increase in tau. So if we increase tau to 6, you see that it just falls on top of this continuous line. If you increase tau to 12, it again falls on top of this continuous line, and tau equals 6 and tau equals 12 also fall on top of each other. So if you did not have the continuous line, you would still know that we have converged. Okay, because tau equals 6 and tau equals 12 would have fallen on top of each other. And for tau equals 6, you require a bath size of 14. For tau equals 12, you require a bath size of 26. Now, you still have points in steps of tau. How do you get the in-between points? You get the in-between points by utilizing this T1. So you rerun this full thing with various values of T1, and you can generate all the in-between points. Okay, so this is so the squares are points that were there here, and we are doing up to only some small time where this in-between points are like more sparse, right? And yeah, so this was the exact line, and then you can reconstruct everything. Now, again, coming back to the question, what we have done here is this continuous line is essentially our exact dynamics in presence of infinite size baths. Okay, we have reconstructed the full dynamics by recursively using this trick with baths only of size 14. Interestingly, for these, and this will not always happen, this is just for this choice of parameters, the bath size is actually smaller than the system size. Okay, we have, and there is no small parameter anywhere, right? System bath coupling is strong and so on. So we have reconstructed the full time evolution in presence of infinite size baths with only using very small bath sizes. Okay, so this is for the non-interacting case. Now, if that V is not 0, then you cannot use this trick of evolving that evolving this matrix. Okay, so this trick does not work, and it requires direct evolution of a mixed state of Hilbert with dimension this, which is ridiculously difficult, right? And its complexity scales exponentially with chain length. So you usually cannot do this, except there are certain tricks you can use, and one of them is tensor network time evolution. So this is has become like one of the standard techniques in some sense. There are many reviews, and these are 3 of them. So let me give a small introduction, like just this is not an introduction, this is just giving a very brief idea of what approximation makes it possible, basically, right? So this idea actually comes not from physics but more from computer science, and that's basically, it's like something like data compression, right? So let's say you have a matrix of dimension d1 cross d2, and the number of elements you would require to obtain this matrix would be d1 times d2, like number of elements that you have to store in your computer would be this. Now let's say you do a singular value decomposition of this matrix, so you can write it like this, and now this so these are the singular values. So this is a diagonal matrix with all the singular values. Now, if the singular values are decaying for some reason, okay, then we can approximate this matrix M by writing, like, instead of keeping all the singular values, we keep only chi of them. Okay, if we do that, then the number of elements that we have to store would be this much. Okay, this can be much smaller than d1 times d2 if chi is much smaller than d2. So this is the idea, and the idea is like, okay, let's do it anyway with a small chi, okay, and look for convergence of the matrix elements, and if we can converge, then it's great. So this chi is called the rank is mainly in and in physics it's often called bond dimension. So rank is usually used in in other applications. So how does this come across in physics actually? So that it comes across with this, this observation that some operators, Hamiltonians and states can be written exactly as a product of low rank or low bond dimension, that is low chi, matrices or tensors. Okay. For example, product states can be written exactly with chi equals 1, and that's the minimum value of chi. Okay. Now on time evolution starting up to a finite time, starting from a product state, okay, the state may still be well approximated by a small chi. Okay. So what we do, the usual trick is that you choose a value of chi, do the evolution, and then increase the value of chi, and again do the same evolution, and then look for convergence like this. Okay. And the converge, if you can converge, the converge result is numerically exact. How has this solved the problem of like exponential Hilbert space is that now the complexity scales linearly with the length of the chain. However, it scales exponentially with the bond dimension required for convergence. Okay, so we have exchanged this thing. But the problem is that the bond dimension required for convergence in unitary evolution typically grows with time and makes long time evolution still intractable. Okay, so but up to some finite time it's very good, but after a long time it's bad. But remember, with this refreshing idea, we only need up to a finite time. We do not ever need a long time. So that's going to be an exponential simplification actually. So this is true for all tensor network time evolution techniques, this kind of idea. Okay, what we use in our numerics that we'll see in a moment is that a modified version of this time evolution by block definition, this TEBD. We call it TEBD in mixed basis. But this idea of refreshing is independent of whatever technique you use. Okay, so let's look at this idea. I mean, whatever I spoke about. Sorry, whatever I spoke about before. In a sort of this is basically just showing what I said in the previous slide. So using this our TEBD in mixed basis, and we are just benchmarking it for, let's say, the non-interacting case where you know the exact result, as we know, as we have seen previously. So the black line is the exact result. So you do this trick with a finite value of chi chosen as 75. So that is the blue line. It matches to some extent, and then it goes. It does not match the black line. Okay, it goes something. You do it with a larger value of chi. It matches for a little bit more longer, and then it shows something. You do it for an even larger value of chi. It matches for a much much longer time, and then it shows something. Okay, so that's the idea. That's how you look for convergence. Okay, but now if you do it with this refreshing idea, and since you're never actually simulating up to a long time, so you can converge with a much smaller. So with chi equals 75, it just converged up to this point previously, right? But with this refreshing idea, you get these red points which already fall on top of this black line. Okay, so you can get away with a much smaller value of bond dimension, and this is, remember, is an exponential simplification because the complexity scales exponentially with the chi required for convergence. Okay, so that's again still a non-interacting case. Now let's go to the the actual challenging problem, which is the interacting case with v equals 1. Now everything is 1 again, right? There is no small parameter. Everything is 1. Okay. So if you for experts, this is an interacting integrable system. If you want results for non-integrable interacting systems, that's also there in the paper. Okay. So again, we want to check this statement, right? So we do a continuous time evolution, that is the right hand side, with a large enough value of chi, which is like 300, and we could do it only up to a time 50, which required a bath size of like 102, so that there is no finite bath size effects. Okay, and then we have this Preb idea with tau equals 6 and tau equals 12. Okay, so these are again the results. Occupation at some site, I could have plotted any other observed system observable also. Right. Again, this continuous line we have for chi equals 150 and then chi equals 300. You can see the similar story, right? This convergence, right? That's the right hand side. The left hand side we have plotted here for tau equals 6, tau equals 12, and t1 equals 0 and t1 equals 3. And you see that these things fall on top of the continuous line already. And also tau equals 6 and tau equals 12 results fall on top of each other. Now, again, note that the bond dimension for tau equals 6 is 75 and bond dimension for tau equals 12 is 125. Now, this is again like just for convergence, right? I mean, we have looked for convergence and it has converged with these bond dimensions. Okay. Once again, 300 to 75 is a big jump, and the complexity scales exponentially with chi, so it's a really big jump. And this shows up in this kind of time for the practical time for simulation, right? So this continuous time plots, okay, in the computer that I was using, in the code that I wrote, it took about 90 hours. That's like 4 days. But doing this refreshing idea with tau equals 6 using the same computer and the same code requires 12 minutes. And if you do with tau equals 12, it requires around 1 hour. Okay. Not only that, if you wanted to continue this continuous line up to a longer time, okay, you would require a much larger bond dimension, and that would basically become intractable. Okay. However, since this refreshing thing has converged already with a small bond dimension, you can continue this thing as long as you want. And you can basically, so this is what I have done. I'm plotting currents in various bonds in this system, right? So like between 4th and the 5th site, between 12th and the 13th site, and so on. And you see basically the plot, and these continuous lines are again from the same simulation as this continuous lines. Okay, so you can just continue this thing up to a long time, and you can, if you don't have these continuous lines, you can still look for convergence just between tau equals 6 and tau equals 12, and you see that they give almost the same results. So that has converged, and you can continue these things up to a long time. And then if you look at the final time point, the currents at various bonds have become almost the same. So that is a signature of the non-equilibrium steady state. So we have reached a non-equilibrium steady state. So we have done a full time evolution up to non-equilibrium steady state of an interacting system in presence of two baths at different finite temperatures and chemical potentials with no small parameter in the Hamiltonian. This is just impossible. This was just impossible before. Like this was just impossible without any refreshing idea. Okay. So that's that's basically the main thing. But till now we have been, let's look at a different thing, a different way. So till now we have been looking at this chain mapping idea, okay, with this mixed basis TEVD and so on, right? But this idea of refreshing is independent of these techniques. In fact, it is also independent of chain mapping, right? So there is this another technique called tempo, which is called time evolving matrix product of. So this is also a tensor network based technique, but this is a very different one. This is a path integral approach. This is based on Feynman-Vernon path integrals, and this actually considers infinite paths. So what it does is it stores the influence functional as a tensor network. Okay, and then to do that, will actually require infinite paths, and you do not. There is no chain mapping. Okay. So this was the paper which introduced this technique, and so the codes for solving exactly spin boson kind of models are available, like this sort of available as a package. Okay, and this is the previous one. I wrote my own code. This is I'm using a package, so I do not know the details of the numerical implementation, but I know the mathematics of it. Okay. So what we are looking at is just a spin boson, so meaning a spin with some frequency and some detuning, right, coupled to a bosonic bath with ohmic spectral density at some temperature. This is like the most canonical open quantum system you can think of. Okay, so with these parameters, you can sort of estimate that the memory time is 3, and that is important in this tempo technique. Okay, so that actually is like inherently appears in the terms of tempo. You have to increase this thing and make it converge, and we are plotting the converge plot. Okay, So, okay, and these are parameters. Again, there is no small parameter actually. Now, again, we have done the same thing for tau equals 6, 12, 25. You see that basically the same story, that tau equals 6 has not, like, with increasing tau, you converge to this continuous line. And the time to the steady state is much longer than the tau required. So basically, whatever we wrote before, it holds. And this is, again, once you have converged, you can use the tau equals 25 again recursively to reconstruct the full dynamics if you want, okay, with different values of T1 now. So this entire trick holds. Now here is the point about unique non-equilibrium steady state. If you had delta equals 0, okay, this model corresponds to something called independent boson model. This model can be exactly solved. However, sigma z is a conserved quantity of the full dynamics, meaning the value of sigma z will not change, meaning the system does not have a unique steady state. In that case, PREV is not guaranteed to work. For this bath, it seems to do reasonably well, even if delta equals 0. However, if you take a superomic bath, it actually does not work. We have checked this. Okay. So this is exactly why you need a unique steady state. I mean, this is an explicit example where you actually see that you need an explicit unique steady state. It can be argued otherwise also, but this is the. And the other thing is, if you are wondering about this, that this model is related to some other problems called Kondo temperature, Kondo physics, and Kondo regime, and so on. So that would be like when at extremely like at even lower temperatures and even higher system bath couplings and so on. Probably this refreshing idea is not going to give any advantage. So as you can see here, the advantage is not so much, right? I mean, we could have used tempo and could have used done the refreshing and so on. The advantage is not too much for this kind of small systems. There is an extreme advantage when you have a scaled up system. When you have a big system with few sides coupled to bus, there is an extreme advantage. That is the problem that was impossible to do before, that can be done now. This kind of problems you could have done using tempo. You could have done using other tricks also, like hierarchical equations of motion. That is the classic technique used to solve these problems. Okay. You could have used the refreshing, you will get a little bit of advantage. If you want to go to the Kondo regime of these problems, you will probably not get any advantage, and I'll explain why. Because yeah, so I'll come to that. But if you have a big system with only few sides coupled to bath, you will get an extreme advantage, and that is the problem that was basically intractable before. Okay. So I want to mention another.
So Archak, 5 more minutes, okay?
Yeah, I'm done almost.
Okay.
So another thing I just want to mention here is if you take this system and if you look at in the energy eigenbasis of the system, right? So okay, one way to think about this problem is you can put this HSV thing inside. You can take this sigma z out, right? So you can think of this thing as some kind of quantum noise coming in the frequency of the qubit due to presence of some bosonic modes. Okay. Now, if you look instead of in the eigenbasis, instead of in this basis, if you look at in the eigenbasis of the system Hamiltonian looks like this. Okay. And the system Markovian looks like this. Now, if you look at some like tau x and tau z and so on in this basis, you will find that in the steady state there is a considerable value of tau x. Okay, so I mean this is the previous same as previous result that's transformed to this basis. Okay, so this is called steady state, what we have been calling like steady state coherence, not related to this work but previous works. Okay, so this is steady state coherence. And so we are also plotting the radius of the Bloch sphere. If you look at the radius of the Bloch sphere, it's also quite close to 1. So steady state is actually quite pure with substantial coherences in energy eigenbasis, right? So this, I mean, sometimes a spin coupled to a bosonic bath is sometimes expected to decohere and so on like that with no coherences and so on, but that's actually not the typical case. If you are coupled to a bath, you will typically have coherences in the energy eigenbasis of the system in the steady state, these coherences are not destroyed, they are created because of coupling to the bath. Okay. This was explored in previous works also by us in a more sort of physical model, but weak system bath coupling in this work. Also, if you want to, even in weak system bath coupling, if you want to describe these coherences from any weak coupling Lindblad equation, that is impossible. That is fundamentally going to give you wrong answers, and that can be shown here. However, if you, for experts, if you use a Redfield equation, something called a Redfield equation, it violates some properties of the density matrix, but it will actually give the correct coherences in a gigantic histolytic model. Okay, so yeah, so that's basically it. Now let's come back to the this refreshing idea, and I'm just talking about some limitations here. So first of all, one limitation is, as I said, it requires existence of a unique steady state, right? But this is typically true in many experimentally relevant situations. But then there are this whole class of other things, like you have this dissipative time crystals and so on, and limit cycles and so on, which basically does not fall in this category, and probably you cannot use this refreshing idea there. Now, if you the more non-Markovian you get, the larger the value of tau you require to converge, and it becomes harder. Now, if that value of tau becomes of the order of time to reach steady state, then you do not get any advantage. And this is exactly what I think will happen if you go down to the Kondo region. Okay, so basically, I mean, formally that result still holds, but it's not useful at all. But if you have a large system with only few sites coupled to baths at finite temperatures, this is not going to happen, and it's going to be super advantageous. And the open questions, basically, this is a very new thing with a lot of interesting features. Not everything is clear to me also. So yeah, this is just the beginning, and there are lots of things to do. So I'll thank my collaborators. This is Javier Pure, from whom I learned everything I know about tensor networks. This is John Gould, Steve Campbell, and Giacomo. Giacomo was in our group before, now he's in Berlin. So yeah, with that, I'd like to thank you for your attention.
Thank you, Archak, for your excellent talk. Let us thank our speaker. And we have time for questions. So perhaps let me start about the computational time. Was this referring to a single CPU, or you did some parallel computing?
No, this is parallelized code in a cluster.
In a cluster.
Yeah.
So it's like how many CPUs order? Like dozens,
so
hundreds?
20.
20.
Yeah.
Mm-hmm.
But my point is, like, whatever is done here is exactly the same, with exactly the same code, same CPU, same everything, right? And there's no difference in architecture or code. It's just recursively using the same code.
Mm-hmm. Okay, thank you. So Juzar has a question or comment.
Thanks. Thanks, Archak, for your talk. So just coming back to this idea of the unique steady state,
yeah,
the model that you showed where the sigma z commutes through, right? Does it have, so a unique steady state? Sorry, does it have two different steady states, or is one of the steady state oscillating in time? So is it a periodic
so
steady?
with delta equals 0, you mean?
That's right.
So okay, I mean, okay, first of all, I think, okay, this is something, again, I'm just telling, okay, we have not done a full analysis of this, but I think, so sigma z is just conserved, right? And only sigma minus will show some I mean, you can basically write this.
Right, so this is a pure dephasing model, right?
Yeah, and sigma minus, you can write down
So the coherences will always oscillate.
No,
no. The populations. Sorry,
the populations are conserved. The coherences are going to decay.
No, coherences will decay. The populations will oscillate.
Be conserved. No, it's conserved, right? Sigma z is conserved. I mean, if delta is 0, sigma z is conserved by the full Hamiltonian.
Okay. So if you start in whatever populations you'll start in, you'll just remain there no matter what.
Yes.
Okay, so the reason why I was asking this was, again, because there can be different types of non-unique steady states as well, right? You can have actually steady states, or you could have oscillating states.
Yeah,
at
here
long
I think there
times.
is no oscillation. This is a particularly simple one. There is no oscillations. I mean, yeah.
Right. So it's not even based on this. You really need a unique steady state for your technique to hold.
So we required a unique steady state to prove this statement.
Yeah, sure.
Yeah. So that's, I mean, now I have a feeling that even in certain classes of cases where you do not have a unique steady state, you might still get away with this, but I'm not sure, and that needs to be explored.
Okay. Okay. All right. Thank you.
Do we have any further questions from the audience? Juzar, do you have further? Your hand is still raised.
Sorry, I just forgot to lower my hand.
Okay. So in this case, I see no raised hands. So let us thank Archak again. And with this, we conclude our today's seminar. So thank you all